Welcome everyone. Now we are going to discuss about the DC circuit analysis. First let us discuss about Ohm's law. Ohm's law is given by V is equal to IR, where V is the voltage, or we can say that it is a potential difference. It is measured in volts, and I is the current, it is measured in ampere, and R is the resistance and it is measured in ohms. For example, a 12 volt battery is connected to a resistor with a resistance of 6 ohms. Then what is the current flowing through the circuit? So here the voltage given is 12 volt and the resistance given is 6 ohm. Hence, in order to find the current, we can rearrange this Ohm's law as I is equal to V by R. Thus, by substituting 12 volt and then 6 ohm in this formula, we will get current as 2 ampere. So this is the Ohm's law. And the next one is Kirchhoff's current law. So Kirchhoff's current law states that any node or junction in an electrical circuit, the sum of all currents entering the node is equal to sum of all currents leaving the node. In other words, we can say that there is no electric charge can accumulate at the node, or the charge that flows into a junction must flow out of it. That is, sum of the incoming currents is equal to sum of the outgoing currents. Summation I in is equal to summation I out. And then the algebraic sum of all currents at the node is actually 0. For example, at a node, a current of 4 ampere is flowing in and a current of 1 ampere is flowing in, and another current I3 is flowing out. What is the value of I3? So by using KCL, we know that sum of the incoming current is equal to sum of the outgoing currents. So here in this node, there are two incoming currents, that is 4 ampere and then 1 ampere, and there is one outgoing current, that is I3. So by adding this 4 and 1, we will get the outgoing current I3. So Kirchhoff's current law, or KCL, it is a cornerstone of circuit analysis, and it is used in conjunction with other laws such as Ohm's law and Kirchhoff's voltage law in order to solve for unknown currents and voltages in complex circuits. This is particularly important for nodal analysis and simplifying circuits, and then for circuit design and troubleshooting also. So it is a more powerful method for solving circuits by applying KCL at each node to create a system of equations. And KCL helps in understanding how current divides in parallel circuits. And also we can use KCL to ensure that a circuit is whether designed properly, and we could able to diagnose the problems by verifying the flow of current at various points. So let's see in another one example. So here we have a 12 volt battery, and then we have three resistors connected here. So here same current will be flowing entirely through this circuit because all the three resistors are connected in series with the voltage source. So here the current flowing through all the three resistors will be same, and then but the voltage between these three resistors will be different. So the entire voltage is actually 12. So this we have indicated by the voltmeter, that is the entire voltage of the three resistors is actually 12. But this 12 volt is actually equally divided between these three resistors as 2.55 and 7.74 and then 1.703. So here the conclusion is that from this figure is that current flowing through a series circuits will be same, but the voltage will be divided. The next is Kirchhoff's voltage law. So Kirchhoff's voltage law states that algebraic sum of all the voltages around a closed loop in a circuit must be equal to 0. So a closed loop is any continuous path in a circuit that starts and ends at the same point without passing through any component or node more than once. So we can say that summation of all the voltages is actually equal to 0. Next we shall see about the mesh analysis. Mesh analysis is a systematic application of Kirchhoff's voltage law to each independent closed loop in a circuit. So mesh is actually a closed loop in a circuit in which we don't have any other loops inside it. So mesh is a separate closed loop. And then mesh current means the method works by defining a circulating and hypothetical current for each mesh. By convention, these currents are typically drawn in the clockwise direction. We can draw it in anti-clockwise direction also, no issues. but we have to ensure that we are defining the current in the proper way. If a current, if resistor is sharing currents between two meshes, then we have to see the direction. If one is in anti-clockwise and one is in clockwise, then the current direction should be opposite. That is, we have to write I1 minus I2. Whereas if it is flows in the same direction, then we can write that I1 plus I2. So a system of equations. For a circuit with n meshes, we will write n independent KVL equations. So suppose if we have 10 meshes, then we have to write 10 KVL equations. If we have 3 meshes, then you have to write 3 KVL equations. Thus, by solving this, we can able to find the mesh currents with the unknown variables. And then the voltage source is simply added or subtracted from the KVL equation depending on whether the mesh current enters its negative or positive terminal first. And then the resistors, it is nothing but a voltage drop across the resistor is found using Ohm's law. If the resistor is shared between two meshes, then voltage drop is based on the difference between the two mesh currents flowing through it. As I told, I1 minus I2 or I1 plus I2 depending upon the mesh current direction what you assumed, either clockwise or anti-clockwise. Thus by solving it, we could able to find the mesh currents, and once the mesh currents are known, the actual current flowing through each branch or each component can be easily found out. We can also find the power, and also we can be able to measure the voltages also. So the limitations is that it is only applicable for the planar circuits. So when wires are crossing, the mesh analysis is little bit difficult. In those cases, it is known as non-planar circuits, and we can go for the loop analysis in order to find it out. And the next, super mesh. So as this is a special consideration, super mesh in the sense it is used when the current source is tagged between two meshes. So this simplifies the analysis by treating two meshes as one larger loop. For example, consider this circuit. Here we have three meshes, and then I'm drawing the current direction in clockwise, and I'm naming it as I1, I2 and then I3. So when KVL is applied to the mesh 1, then we can write equation as 10 minus 1 I1 minus 3 I1 minus I2 minus 6 I1 minus I3 equal to 0. Thus by simplifying this, we will get 10 I1 minus 3 I2 minus 6 I3 equal to 10. And then applying KVL to mesh 2, minus 3 of I2 minus I1 minus 2 into I2 minus 5 I2 minus 5 is equal to 0. Thus by simplifying this, we will get minus 3 I1 plus 10 I2 equal to minus 5. And then applying KVL to mesh 3, we can write it as minus 6 of I3 minus I1 plus 5 minus 4 into I3 plus 20. Thus by simplifying this, we can write minus 6 I1 plus 10 I3 equal to 25. So by solving all these three equations, we will get I1 is equal to 4.27 ampere and I2 is 0.78 ampere and I3 is 5.06 ampere. Suppose these are the currents between currents of I1, I2 and then I3. Suppose if I want to find the value of current flowing through the 3 ohm resistor, then the I1 is actually flowing in clockwise and I2 is also flowing in clockwise. But when we see in the resistor, it is like opposite direction it is flowing. Hence it has to be subtracted in this way, like 3 into I1 minus I2. So the current flowing through 3 ohm resistor will be equal to 4.27 minus 0.78. So that is how we have to calculate in order to find the current flowing through the resistor if the current direction is different, whereas this resistor is shared between the two meshes. Similarly for 6 ohm also. Whereas for 4 ohm, 5 ohm and 2 ohm, it is not sharing any meshes. So the corresponding current values is applicable, or it will be flowing through this resistors. Similarly in 1 ohm resistor also. The next is nodal analysis. It is a direct application of Kirchhoff's current law. So which states that sum of the current entering the node is 0. So here our aim is to find the unknown voltages at each node of the circuit relative to the chosen reference node. What we have to do is, all connection points in a circuit are identified as nodes. So one is selected as the reference node, that is 0 volt. And then we have to write the KCL equation. A KCL equation is written for each non-reference node with the currents expressed in terms of node voltages and resistances. That is using Ohm's law, I is equal to V by R. Then we have to solve for the voltages. So this creates a system of linear equations that are solved simultaneously in order to find the voltages at the each node. So here there is a special condition like supernode. It is a technique used when a voltage source exists between two non-reference nodes, simplifying the KCL equation for that part of the circuit. So nodal analysis is often preferred over mesh analysis because when a circuit has fewer nodes than meshes, or when it contains current sources, it is easy to find the values when if we use in the nodal analysis more than the mesh analysis. You can look into a circuit which is given here. So here we have one voltage source and one current source, and then here we have three nodes, node 1, node 2 and then node 3. So then voltage at node 1 is denoted as V1, and voltage at node 2 is denoted as V2, and voltage at node 3 is denoted as V3. So by applying KVL at node 1, we can write it as V1 minus 20 divided by 3 plus V1 minus 2 by 1 plus V1 minus V3 divided by 2 is equal to 0. So thus by simplifying this, we can write 1.83 V1 minus V2 minus 0.5 V3 equal to 6.67. And then by applying KCL at node 2, we can write that V2 minus V1 divided by 1 plus V2 minus V3 divided by 6 is equal to 5. And then by simplifying this, we can write minus V1 plus 1.72 V2 minus 0.17 V3 equal to 5. And then by applying KCL to the node 3, we can write that V3 minus V1 divided by 2 plus V3 by 5 plus V3 minus V2 divided by 6 is equal to 0. Thus by simplifying this, we can write minus 0.5 V1 minus 0.17 V2 plus 0.87 V3 equal to 0. So by solving this, we can write V1 is equal to 23.82 volt, V2 equal to 27.2 and V3 equal to 19.0. So after finding this value of V1, V2 and V3, we can able to find the current flowing through each of these resistors very easily, and also we can find the power across the each resistor or the load. So these are about the DC circuit analysis. Thank you.